Hello, welcome to another Stat 510 video. This video will mostly be an extension of the last video. Um, in that video, we were talking about parametric inference, and in particular, within parametric inference, we were saying, well, we have these parameters we want to estimate. How do we estimate them? And the ways that we looked at for doing that were method of moments and maximum likelihood. But just a bit of a refresher, what we were doing there more generally was point estimation, right? So we have some fixed but unknown parameter, and we want to use a statistic that is some function of the data to serve as an estimator for that value. And something we sort of hinted at but didn't actually do was this notion of considering the sampling distributions of the estimators that we came up with. Why would we want to do something like that? Well, if we know the sampling distribution of the estimator, well, then we can develop an interval estimate instead of just a point estimate, which we would rather do because we understand that we're making this estimation under uncertainty. Okay, so the first way we looked at doing that was method of moments. I won't linger on this too long, but here we're just defining the parameters, the population moments and the sample moments. And then what we did was we said, okay, well, however many parameters you have, say you have k parameters you want to estimate, find the first k moments, equate them to the first k sample moments, and then solve for those k parameters that you're interested in, because we now have k equations, k unknowns, and we can do that. So that was method of moments. And related to method of moments, now I'm just going to briefly talk about a few properties. So if we have some theta hat, that is the method of moments estimator for theta, then under some appropriate conditions, theta hat exists with probability tending towards 1. So I'll call this existence. So we have some reassurance that, for the most part, this estimator should exist. We also see that it is consistent. And lastly, it is asymptotically normal. So theta here could be vector valued. So we have the variance here represented by sigma. The exact specification, I'll say, is given in the book. But it's not the easiest thing in the world to deal with. So a faster way would be the bootstrap. Okay, but we're actually going to focus instead on maximum likelihood. And I'm realizing now as I do this that I don't have a recap slide for what maximum likelihood is. But in short, you write down the likelihood and then you maximize it. Okay. And after last homework, you're probably sick of doing that. I can't say you're not going to do it more, but I feel like you don't need me to recap that. Okay, so thinking about some properties of maximum likelihood. It is also consistent. We actually talked about this next one last time. That is the fact that the MLE is equivariant. So what that means is that if theta hat is MLE for theta, then if we have some function g of theta hat is the MLE for g of theta. So we sort of already dealt with this one a good deal last time, although that will play into something we do later in this video. Okay, so the MLE is also asymptotically normal, except it has a nice property where this estimated standard error here, we can get an analytic formulation of that, that'll still give us this approximate normality. And that's going to be a big focus of what we talk about in this video. We're going to argue that the MLE is efficient for large samples. We'll sort of leave explanation of that one until we get there. And then one last note that the book makes about properties of MLEs is that the MLE is approximately the Bayes estimator. We're going to delay talking about that until we get into chapter 12 of the book because we'd have to introduce what that is, but we'll find later on that this is a nice property. Now, I should say that these 5 properties all assume something that we call regularity conditions. We're going to sort of just tacitly assume that these are always true, but you should be aware that that's something that we're assuming here. And effectively, they're saying that like the density that we're dealing with is, smooth in some sense. But we're not going to focus on that. Okay, so let's dive into talking about some of these. So first, I need to define some things. So first, we want to talk about the score function. So the score function here, it's the derivative with respect to theta of the log of the density. So we're just dealing with a random variable x here. We're not dealing with a sample of data yet. And then if we move on to having a sample of data x1 through xn, we can talk about the Fisher information that sample gives us, that is about the parameter that we're interested in, theta. So you'll notice that it's a function of the score function. In particular, it's the variance of the sum of the scores. And then because of independence, we can swap the sum and the variance there. So that is the Fisher information given by that data for that parameter. Okay. Right. So working with Fisher information, sometimes if we're considering the n equals 1 case, that is, we just have a single x, we don't necessarily have a sample yet, we denote that like this. Basically, we drop the subscript. And here we see another way of calculating that. So it's the negative expectation of the second derivative of the log of the density. And so this is generally, this right here is generally a useful way to calculate the information given by a single observation. But it turns out, when we're dealing with the IID case, the information of a sample of size n is equal to n times the information of that single observation. I'll put the 1 here to make that really clear. And again, this is for the IID case. So basically, instead of directly calculating this thing here, you would do this instead, and then simply multiply by n, because that'll make things much easier. Okay, so why do we care about this? So at the moment, I've just defined some things because, but what does this do for us? Well, it turns out it's related to the large sample normality of the MLE. So again, notationally, and I think I've said I'm not a fan of this before, the standard error is the square root of the variance of the estimator. This is just the standard deviation of the estimator, but we're going to call it the standard error. Okay, so it turns out that the standard error is approximately the square root of 1 over the information given by the sample. And furthermore, if you take the estimator, subtract its mean, divide by the standard error, well, then that thing is standard, it converges in distribution to standard normal. Now, there is one issue here, which is that this is all well and good, but this is a function of the parameter. So it turns out that if we simply plug in the MLE for that parameter, we get the estimated standard error, which is approximately this. It's not a great hat. That's a better hat. Okay, and we get something like this. Call that SE hat. So all that is to say is that the MLE, sometimes I drop the sub n. The MLE is approximately normal with mean the true value of the parameter and the estimated standard error that we calculate. Okay, so that's really useful. So if you have a large sample, the MLE is approximately normal, even if you plug in the estimated MLE to the standard error. That's great, because it gives us a way to create confidence intervals. So take your estimate, do plus minus critical value times standard error. So in this case, if we define the interval this way, then the probability that the parameter is contained in that interval goes to 1 minus alpha as n goes to infinity. So in a large sample sense, we can make confidence intervals. So stated much more succinctly, if we take theta hat sub n, which is MLD, do plus minus 2 times the estimated standard error, this is an approximate 95% CI. And remember, this is I like to call this 2. It's 1.96. You know, it's the relevant critical value here. We often just say 2 because we're approximating anyway. Okay, cool. So in other words, an MLE is a really general tool for estimating parameters, and with those estimates, we can very easily, if we have a large sample, create an approximate 95% or really any percentage confidence interval that we want. That's pretty nice. Okay, so let's try to do an example. So possibly the most basic setup we could think of, we have x1 through xn that are IID Bernoullis with some probability of success p. Here we see the MLE. I'm not going to go through that derivation, but it shouldn't be a surprise that the MLE is just the proportion of ones in the data set. Okay, cool. So I've also written out the probability mass function and then the log of that probability mass function. So what I ultimately want to do is I want to derive an approximate 95% confidence interval for P. So let's do that. So if we sort of think about what we need to do here, I'm obviously going to need to calculate this estimated standard error, which means I'm going to need to calculate the Fisher information, which means that I'm probably going to calculate the Fisher information for a single random variable x. Okay, so calculate the score function, calculate Fisher information for a single observation, then calculate the Fisher information for the whole sample, then calculate the standard error, and then do the usual thing to make the confidence interval. So that's roughly what we're going to do. Okay, so first up, the score function. Okay, so that is defined to be the derivative with respect to the parameter, something like this. Let's see here. So I think that should be something like x over p minus x minus 1 over 1 minus p. Does that look good? Yeah, okay. All right. So then, let's see. Going back here, it looks like I need to take a derivative, right? Yes. Oh, sorry. I confused myself there for a second, and I realized that I'm looking at something and scrolling I have to scroll on two screens simultaneously. So so notice that the score function is one derivative, but then to do what I said we needed to do, we actually need to take two derivatives. So what we really need, this here is equivalent to the derivative of the score function. Okay, so all that to say, I want to take a derivative of the score function. Let's see if I can do that. So I think it would be something like, oh, here, let's write this out actually. This is part that I don't have in my notes that would have made me less confused. Okay, so that's what I want to do. So I think it's something like minus x over p squared plus x minus 1 all over 1 minus p squared. Okay, cool. All right. Then what do I need to do? Oh, I want to look at the negative of this. So I'll put a negative here. I'll put a negative here. We'll change this to a plus, and we'll change this to a minus. Right. Okay. So what I need to do then, to find the information of a single observation about p, it would simply be the expected value of the negative derivative of the score function with respect to this. Okay. And then, so due to the linearity of expectation, the expected value of x here, the expected value of x here, those would both be p's. So we get, oh, sorry. Missed a squared there. I thought I was going to go wrong. So we get something like, what did I say? P over p squared minus x minus 1 all over, no, the x becomes a p. That was the whole point of this. 1 minus p squared. Okay, let me just check my work real quick. I think that all looks good. So this ultimately becomes 1 over p times 1 minus p. Okay, and just to reiterate, this expression here is the same as this expression here. I suppose I should have made that more clear on this slide here, but hopefully that is clear now through this example. Okay, so I have the information for an individual observation, but now I want the information provided by the whole sample. That is this. So what we said was, because we're dealing with an IID random sample here, this is n times the information given by a single observation. So that is n times the thing that we found. Okay, cool. All right, so next we need a standard error. So first we'll find the actual standard error. So the standard error is approximately 1 over the information given by the whole sample, which I believe should be p times 1 minus p all over n square root. And hey, that should look pretty familiar. We've seen this before, but now we have sort of a reason why this exists. But we don't know p, right? So estimate it with the MLE, so this will become the estimated standard error. So we plug in the estimated value. Okay. So then, to get an approximate 95% CI, we'll simply take the MLE plus or minus 2 because we're being lazy, times the square root of p hat times 1 minus p hat all over n. Okay. And that shouldn't have been a big surprise. That's, an interval that you've seen before. This is just a new justification for it. I mean, realistically, we didn't need to do all of this because, we could have just looked at this estimator without knowing that it was an MLE and said, oh, well, apply the central limit theorem, get approximate normality, get a confidence interval, and we would have gotten the same thing. But again, this works for all MLEs. We just happen to pick one that is easy to work with, and also we could have applied the central limit theorem, but that won't always be the case. So that's why this is so powerful. Okay. So moving towards talking about efficiency. So let's say we had two estimators, T sub n and U sub n, both trying to estimate the quantity theta. And let's say it turned out that they could both be shown to be approximately normal. That is in a limiting sense. And we see Tn has a limiting normal with variance t squared, and Un has a limiting normal with variance u squared. So we can define this concept called asymptotic relative efficiency. And essentially, the asymptotic relative... meet my words here. The asymptotic relative efficiency of u to t is defined by this expression here, where we end up with t squared over u squared. So essentially, we're looking at a ratio of the limiting variances. And so if this value is low, that would mean that t has a smaller variance than u. Therefore, it's a better estimator in a limiting sense. Okay, so a quick example of this. So suppose we're in the good old situation where we have x1 through xn, normal with mean theta variance sigma squared, and let's look at two different estimators. So the first estimator we're going to look at for theta is the MLE, and we happen to know the limiting distribution of that. We've seen it, a million times already. So then we're going to look at a different estimator. We'll look at theta tilde, which we will define to be the sample median. And we won't show this, but it turns out that you could show that this also has an asymptotic normality with a slightly different variance. That is, it's pi over 2 times sigma squared. Okay. So, but then we can look at the asymptotic relative efficiency of theta tilde to theta hat. That is another bad hat. Much better hat. Okay. So that would be the variance of this one divided by like this. I'm not too good at math, but I think the sigmas cancel, and we get 2 over pi, which is something like close to 0.63. And I want to note that this is less than 1. And that's because the variance for the MLE is smaller than the variance for the median. Okay, cool. And it turns out that this is not true just in this individual case, but this is true in general for MLEs. So that is, suppose we have theta hat, which is an MLE, and we have theta tilde that is pretty much any other estimator. Well, then the asymptotic relative efficiency of, I don't know why I did a square bracket there, not that it matters, of that other estimator, that looks like a hat, but it's a tilde, to the MLE. Let's note that because my parameter decorations have been really bad here. This thing is less than or equal to 1. So what this is saying is that in large sample settings, the MLE is going to outperform a lot of other estimators because we want estimators with low variances. And this is saying that the MLE is going to get us that relative to other estimators. So that's really good. And that's this idea of efficiency. Okay. All right. So one more idea that we've really seen before, but we're just going to reapply it here. And we'll sort of mention why we need this thing. Maybe not why, but why it comes up a lot. We already knew why we needed it. Okay, so we're going to talk about the delta method again. So here we have tau is defined to be some function of theta. And we're going to assume that g is differentiable and the derivative of g at theta is not equal to 0. But let's also think, well, theta hat is the MLE for theta. And that means that the MLE for tau is g of theta hat. Well, turns out that we can show that the estimator for tau, that is the MLE for tau, is also asymptotically normal because it's an MLE via equivariance, but it's an MLE, therefore it's asymptotically normal. But the thing we need then is how do we get the standard error of tau now? And that's where the delta method comes in handy here. So we would get g prime theta, the absolute value of that, times the standard error of theta hat. I cannot draw a hat to save my life tonight. Hat. Okay. And then, like we've seen so many times before, well, we don't know theta, so plug in everywhere you need to, and that would get us the estimated standard error of tau. And then what can we do with this? Well, you guessed it. So if we take the MLE of tau plus minus 2 times the estimated standard error of tau, this is an approximate 95% CI. Cool. So let's do an example. All right. So in this example, we're going to assume we have a random sample that is from a normal distribution, but we're going to assume that mu is known and sigma will be the unknown that we're interested in estimating. But actually, what we want to estimate is some function of sigma. Yeah. So, okay. So what I have here is I wrote down the log likelihood. This goofy symbol here is what I call some stuff, which would make the log likelihood. There's, you're probably wondering yourself, hey, where did that like 2 pi in the density of the normal go? It's in the sum stuff. And we put it in some stuff because when we take the derivative and do all that stuff, it's going to go away, so we don't really care about it. Anyway, long story short, if we went through all that procedure, this would be the MLE for theta. Not theta, sigma. And we're trying to estimate psi here. Okay, so I also have the log of the density here. And again, I have some stuff here. Again, that's where like that 2 pi is going to be because we're about to take a derivative and it's going to go away. So I'm not too worried about it. Okay. Speaking of those derivatives, here they are. So I started with the log of the density. Then I took a derivative with respect to sigma. Then I took another derivative with respect to sigma. Hopefully you see why I'm doing this, which is because I want the information of a single observation that it gives us for sigma. I keep wanting to say theta, sigma. So that is negative expected value of that second derivative that I have there. So that's plugging in this here. Okay, quick aside, remember that the expected value of x minus mu squared is literally defined to be the variance of x, which in this problem is sigma squared. So due to linearity of expectation, I think what we're going to end up with here is minus 1 over sigma squared plus 3 sigma squared all over, sigma to the 4th. And then due to arithmetic, we end up with 2 over sigma squared. Okay, but we have an entire sample, not just one observation. So the information that we get from that is what? So it's n times the previous information that we got. So that should be 2n over sigma squared. Great. All right. Sorry. Just to mention where we're going, because I don't think I even said we want a 95% CI for this new parameter that's a function of sigma right here. That's where we're going. But the intermediate step is going to be to first get a standard error for sigma, which is, I believe, what I intend to do on this blank page. It's exactly what I intend to do. So I want to get the standard error for the MLE of sigma. So that's approximately 1, not I, 1 over the information for sigma, which should be sigma divided by square root of 2n. That is, I'm flipping this and taking a square root. That's how we're getting there. Okay. Right. Okay, so remember the parameter that we're actually after is some function of this. Oh, I should also say that if we put a hat here and a hat here and a hat here, we're still cool. Right, what was I saying? So this is, the problem told us this. So that means that G prime is 1 over sigma, I believe. So that means that the standard error of the thing we actually care about, we should maybe mention that the MLE here is the log of the MLE for sigma. I guess we're going to need that in a second. But anyway, so the standard error is then the absolute value of 1 over sigma times the standard error of sigma. And, well, we want an estimate of that, so we plug in estimates there. And then, so what do we get? We get the MLE plus minus 2 times this standard error that we just calculated. Oh, I guess I should say that this is what? 1 over square root of 2n. So times 1 over square root of 2n. Okay, cool. All right, so that was an example of the delta method. I realize you can't see all of what I wrote, but I have a feeling you know that it says an approximate 95% CI. Okay, so just wrapping up real quick. So all the examples we looked at right here, there was only one parameter. If you had 2 parameters, you need to do a little bit more work, and you would need to use a Fisher information matrix. And the definition of that is given in the book. You'll need to do it on one homework problem. But I submit that if you know how to do it for one and you can follow a definition, you'll be able to do it for a multi-parameter case. Please let me know if I'm wrong. And then related to that, there's also a multi-parameter delta method. But again, the form of it looks very similar to what we saw in the single parameter case, so I'm confident that you'll be able to tackle that. Okay, so these 2 items here will be relevant to the challenge problem for this week. So I have skipped talking about sufficiency and the factorization theorem. Kind of a more old school, kind of more boring topic, but it is useful. Which is in the appendix of the reading this week. So I would recommend that you have a look at that because you need to, you'll need this for the challenge problem, and it'll be somewhat related to using the Raoul-Blackwell theorem to create an estimator for that problem. And then sort of related to the factorization theorem, there's this notion of exponential families, but we're not going to use that in this class, so I also leave that as optional reading in the appendix if you're interested. Okay, I have space in there for a second. All right. Yeah, that's it. So probably not too much content this week, but a good amount of problems, and I think that's the more important thing. So yeah, As always, if you made it to the end of the video, good job, and I'll see you in the next one.